Hi, in part 4 we're going to look at some applications of further mathematical induction. In these applications we'll split it into two parts. So first of all we'll look at inequalities in this video, and then we'll have a look at some calculus identities, proving calculus identities with induction in the second video. But for now, let's just revisit some results that we've seen previously to do with inequalities, and then we'll also do an example. So for this inequalities review, just keep in mind that the letters A, B, C, D that we'll use, they're all real numbers. So first up, A is greater than B if A minus B is greater than 0. So often when we want to prove an inequality such as this, it can actually be easier to prove this. And think about this for a sec. This makes sense, right? Whenever we get the difference between two values, if we end up with a positive result, then the first must be bigger or greater than the second. Alright, second. If A is greater than B, and then B is greater than C, then it makes sense that A, what we started with, must be greater than C. Okay, this one can actually be quite useful in a lot of inequality proofs that we do. Number 3. If A is greater than B and C is greater than D, then the addition of A and C will be greater than the addition of B and D. Cool, no further explanation needed for that one. Number 4. If we're dealing with positive values, so A, B and C are all greater than 0, and we have A is greater than B, then multiplying both sides of that inequality by some positive value C preserves the inequality. So AC will be greater than BC. And number 5, if we have A greater than B, and they're actually both positive, right, because they're both greater than 0, then when we take the reciprocal of both sides, so 1 on A and 1 on B, our inequality sign actually flips. So 1 on A becomes less than 1 on B. Okay, so there are our 5 points for our inequalities review. And while they're all relatively simple results, they can be used to prove sort of harder inequalities. They can be quite powerful. So let's jump into our example. Prove by mathematical induction that 2 to the power of n is greater than n squared. And this is for all values of n that are natural numbers, or is it all values of n? I mean, think about what would happen when n equals 1, or n equals 2, or n equals 3. Is 2 cubed, which is 8, greater than 3 squared, which is 9? No, so this one actually has a qualifier that n must be greater than or equal to 5. So that'll be our starting point for step 1. So prove true for n equals 5. Let's start with our left-hand side, which is 2 to the power of n, but we are setting n equal to 5. And 2 to the power of 5, that is 32. What about the right hand side? Well, that's n squared. We're making n 5. 5 squared is 25. So we can see that 32 is greater than 25. Therefore, it is true for n equals 5. Alright, let's go on to step 2. Assume true for n equals k. So, what was it? 2 to the n, so we're going to say 2 to the k, is greater than n squared, so k squared. Alright, that was pretty easy. Let's go on to step 3. The fun part. Prove true for n equals k plus 1. So let's write out what we're required to prove first of all. So we are required to prove that 2 to the power of k plus 1 is greater than k plus 1 all squared. And like usual, we'll start with the left-hand side and see what we can do with this. So the left-hand side is 2 to the power of k plus 1. Now, keep in mind that we want to use step 2. Step 2 involves the 2 to the power of k. So when we look at 2 to the power of k plus 1, well, this is 2 to the power of k times 2 to the power of 1. Or we could write that as 2 times 2 to the power of k if we switch them around. So how are we going to use this? Well, essentially we're going to use that result from our review that states if we have some a greater than b and then b greater than c, it follows that a must be greater than c. We're going to use that idea now. So when we substitute out the 2 to the power of k with our k squared, we know that this term will be greater than the line we're about to write next. So that's this is like our a. Then when we do our substitution, it's like we'll have our b, and if we can show that that is then greater than our c, it follows that a is greater than c. So let's give ourselves a bit more room. And let's make the substitution. So we're replacing 2 to the power of k with k squared. But 2 to the power of k is greater than k squared. So we can put a greater than sign. Technically, I suppose we're using one of our other results here, which is that if a is greater than b, when we multiply both of these by a positive constant, then AC is still greater than BC. So they've both got this positive constant of 2. And even though really we can see that 2 to the power of k is greater than k squared, this constant of 2 doesn't affect it that much, so we can still use our inequality sign. And remember, it's always a good idea to state that we've used step 2. Okay, so how do we now show that 2 lots of k squared is greater than k plus 1 all squared? Well, let's consider the right-hand side. When this gets expanded out, we'll have k squared plus 2k plus 1, because it's a perfect square. And this has got 2 lots of k squared, so there's something in common there. They've both got at least 1 lot of k squared. So if we think of this left-hand side as 1 lot of k squared plus another 1 lot of k squared, then we can just focus on trying to show that k squared is greater than 2k plus 1, because that's the missing part from in here. So let's write that out. So we want to show that k squared is greater than 2k plus 1. Right, is that true? And this is something that we can consider graphically. So let's just do a quick little sketch. So 2k plus 1 is just a straight line. So it has a gradient of 2 and a y-intercept of 1. And then k squared, let's do this in a different colour, is just a simple parabola. Now, I guess the question is, where do you get the point of intersection? Right, what's this point here? Where does k squared start becoming greater than 2k plus 1? And we could go and solve this, right? We could say, where is k squared actually equal to 2k plus 1? and we could just use the quadratic formula. Or we could just think about a few different values, since remember our k and our n values all have to be natural numbers. So when k equals 1, we can see that this is not true. When k equals 2, okay, it's not true. When k equals 3, 3 squared is 9. Is that greater than 2 lots of 3 plus 1? Yeah. And then we can think back to the start of our question all up, is that our n or our k values have to be greater than or equal to 5. So if we've just seen that at 3, it's definitely true. So when k equals 3, we get 9 is greater than 7. That's true. So it's definitely going to be true for 5. Any value after 3, it's going to be true. This statement here. Okay, so k squared is greater than 2k plus 1 when you consider all the values of k greater than or equal to 5, which means we can come back over here and say that k squared plus k squared is greater than k squared plus 2k plus 1. Right? If we replace k squared with 2k plus 1, then this line here must be greater than this line here. But why are we doing this again? Well, remember that k squared plus 2k plus 1, that is just k plus 1 all squared, which is the right-hand side that we're trying to get to. So we're done. Right? We can say that this is equal to k plus 1 all squared, and if we follow the working down with these greater than signs in here, we see that the left-hand side must be greater than the right-hand side. And so therefore, 2 to the power of k plus 1 is greater than k plus 1 all squared. And so therefore, this is true for n equals k plus 1. Now, just to note, this was a very rough sketch back over here. Okay, very rough sketch. So I know when you look at this 1, 2, 3, it looks like the point of intersection is a bit after 3. But if you go and solve it, you get around 1 plus, you get 1 plus the square root of 2 exactly. So you could do this algebraically, of course, if you'd like, and you get around 2.4 as the intersection value. So just take this diagram with a pinch of salt, right? Okay, so now that we've shown this is true for n equals k plus 1, we can write our final statement. By mathematical induction, 2 to the power of n is greater than n squared for all n belonging to the natural numbers, but where n is greater than or equal to 5.